Hi, I'm Tyga Anderson. Welcome back to our series on SKNA Analysis. This episode will be focusing on setting up Labchart Pro. We'll start by opening Labchart and opening the file that we want to analyze. So I have my file stored here, and you'll notice that on the bottom right corner we're set to Labchart file. The raw EDF file produced by Pharos is in a EDF format, or a European data format. Now that I've found my file, I'll select it. For this analysis, we only need the ECG channel. Later on in the series, we'll go over postural analysis, in which we'll be able to use the accelerometer data. Now that the data is loaded, we can start exploring our data. The first step always is to go to the bottom bar and to right-click and select Time Mode. We can set it as Show as Time of Day, and that way we know exactly when this recording occurred. Looks like this recording was taken around 10:29 on June 1st, 2021. And so we can also explore our raw recording a little bit by grabbing the left bar and dragging up. We can also change the zoom by selecting plus or minus. And we can also change the zoom by changing the frame by 10:1 or 20:1 or 50:1 or 100:1. We can get a better look at our data. Now we can start setting up the various channels that we're going to use. So we can go to Channel Settings, and from our one raw ECG channel, we're going to derive 5 additional channels for a total of 6 channels. So with this first ECG channel, it's important to do a units conversion before we begin. We're going to do 1:1 and 2:2, and we're going to look for the unit of microvolts. I don't see the unit here, so we'll have to create it. Now that we've set our units, we can move on to our first channel. Our first channel we're going to call filtered ECG. With this channel, we're going to apply a bandwidth filter by selecting digital filter, and the source channel is going to be the raw ECG channel. And instead of low pass, we're going to select band pass with a low cutoff frequency of 0.5 and a high cutoff frequency of 150. So sometimes you'll notice in Labchart we can't really see things very well. We can either manually adjust by selecting plus and minus, or an easy way to put things into frame is to select this button here to auto scale. So we can see the ECG channel clearly now, and we've filtered out some of the motion artifacts. So you'll notice in the top line it'll waver. But since we've applied a bandwidth filter, it'll apply much straighter on the filtered ECG channel. Our next channel we'll call filtered SKNA. SKNA represents sympathetic or skin sympathetic nerve activity. We'll also apply a digital filter to this using our raw ECG channel, using a high pass filter of 300 Hz. Again, we can't see very much, and we could manually adjust, or we could just select auto scale. Here we can see a couple of nerve bursts right here and right here. The next channel we want to identify is called integrated SKNA, or iSKNA for short. To set up this channel, we'll select integral, from the filtered SKNA channel this time, and we'll select absolute value, time constant decay, and 0.1 seconds. This is consistent with microneurography settings. And our next channel, we'll set up a channel called average SKNA, which we can denote as ASKNA for short. This time we'll use arithmetic, and we'll use the smooth sec function, and inside that function we'll use the absolute function, and we'll use the channel 3, or the filtered SKNA channel that we set up before, and we'll also include a comma 5 in our equation to smooth out every 5 seconds. And our last channel will be the heart rate channel. So I'll denote heart rate. For the heart rate channel, I'm going to use cyclic measurements. We'll use our filtered ECG channel as the source, and we'll use the preset for human. We can see here it's counting the beats pretty accurately, but I'll demonstrate how we can be more sensitive or less sensitive in counting beats. When we raise the standard deviation for the minimum peak height, it becomes less sensitive and it counts less beats. You can see here the little circles are far and few between. When we decrease the standard deviation of minimum peak height, it starts to count more beats and more beats and more. We find that 1.6 is a good place to start, but it's dependent on each recording, so you should always take a look at this. Now that I've selected OK, we can see the heart rate channel down here. Now exploring our data a little bit, I notice here it cuts out a frame, so I'm going to auto scale here as well. But I notice a big burst around here, and I notice a heart rate acceleration preceding the big burst. That's a typical thing that we see in this sort of SKNA analysis. Now that we've set up all 6 channels, we can explore our data. So we can always look at our data more granular by zooming in or scaling in. We can always take a step out and see what it looks like when we zoom out. Generally, there's a lot of noise at the beginning and at the end of the recordings. So one thing we could do is to save a selection instead of analyzing the noise at the beginning and the end of a recording. So I'm going to select around 10:30 a.m. And you'll notice at the end of the recording there's a lot of noise. And this is because this patient took off their Pharos monitor and the monitor kept recording even after the patient took the monitor off. So I'll try to find the point where the patient took the monitor off. And it looks like it was around 10:21 a.m. the next day on June 2nd. So I'm going to hold down the Shift button and click, and that'll highlight all the good usable data that we have. In the top left corner at File, I'm going to save selection. I'm going to save the selection where I saved my raw file, and you'll see at the end it'll write SEL, denoting selection. You could do this step after setting up all the channel settings, or you could do this step before setting up all the channel settings. It's up to you. So that's how you set up Labchart Pro. I hope you found this video helpful. In the next episode, we'll be able to use these settings to extract data and do SKNA analysis.